In this section, we're going to look at some methods where derivatives are used to approximate hard-to-evaluate functions and solve equations that can't easily be solved using traditional methods. We had in the past seen that the tangent line to a function and the graph of a function lie very close to each other. In fact, if we zoom in, we'll notice that the closer we get to the point of tangency, the closer the tangent line gets to the graph of the function. This means that we can use the equation for the tangent line to approximate the value of the function when our values or points are very close to the point of tangency. And we can also use that fact to solve some equations involving our function. Let's start with familiarizing ourselves with some terminology. If you recall, the slope of the tangent line to the graph of the function at a point a comma f of a can be found by just taking the derivative of the function and evaluating that a. And that allows us to write an equation of the tangent line. We can write in the point slope form y minus y1 or f of a equals m, which is f prime of a, times x minus a, and maybe rewrite it moving the f of a to the other side so we have an equation solved for y. So y is equal to f of a plus f prime of a times x minus a. That means, based on what we saw when we zoomed in, that the value of the function when I'm near the point a comma f of a is very close to the value of the line. And I can use the equation of that line, which is easier to evaluate. It's a linear equation, there are no exponents involved, to approximate the value of the function. We call that the tangent line approximation or the linear approximation to the function. And we can write the equation of our tangent line as L of x equals f of a plus f prime of a times x minus a, and we refer to this as the linearization of f of x at a. Let's look at an example. Here we want to find the linearization for the function f of x equals e to the x minus 1 at 1. And then use that equation to approximate what f of 1.2 is. F of 1.2 is e to the 1.2 minus 1, or e to the 0.2. So once we have our approximation, we can find out what e to the 0.2 is without having to use a calculator. Right? So to start with, I need to know what a is, which in this case, I'm told that I need the linearization at 1. So a is 1. And then we need to find f of a. F of 1 is e to the 1 minus 1, or e to the 0. That's 1. So we're looking at the point 1 comma 1. And we're going to find the tangent line at that point. We need its slope. So take the derivative. Derivative of e to the x minus 1 remains e to the x minus 1. And then when we find f prime of a, or f prime of 1, have e to the 0. And that gives me 1. And that lets me write my linearization for my function f of a plus f prime of a times x minus a. 1 plus 1 times x minus 1. And that can be cleaned up. We can distribute the 1 and simplify. We just get L of x is equal to x. Right? So we're asked to use this equation to approximate f of 1.2. So we already know that L of 1.2 remains 1.2, means f of 1.2 is approximately 1.2, right? So the line is going to be an approximation to my function as long as I'm near the value of a. And in this case, 1.2 is pretty close to 1. So we can use that linearization to approximate the value of our function, right? So in other words, e of 0.2, right? That's what f of 1.2 would give me. If I plug 1.2 in my function, I get e to the 1.2 minus 1, or e to the 0.2. E to the 0.2, according to this approximation, should be roughly 1.2. So we've done all of this without a calculator. We've figured out what e to the 0.2 is, and we can then verify it. If you plug in e to the 0.2 in your calculator, you'll see that e to the 0.2 is exactly 1.221402758, and on and on and on. Right? So our approximation isn't terrible. It's accurate to within 1 decimal point. Next, we're going to look at Newton's method, which is a numerical method for us to solve equations, specifically to find the x-intercepts for functions. So what we are going to do is use a linear approximation and the x-intercept for our tangent line to find out where our graph crosses the x-axis. Right? And to do that, we are going to start with any tangent to our graph. So in this case, we are using this value x sub 0, which is over here, and go ahead and find a tangent to our graph. And the red line is, here is our tangent line, and find its x-intercept. And we're going to go through the process of how that's done, but for now, I just want to focus on the concept. And look at that x-intercept. And we'll notice that that's not a very good approximation to our solution at all. So what we'll do is then use this new point and go to our graph and draw a new tangent here. So, and then look at the x-intercept for this new tangent. And if that is not a good enough solution, we'll continue doing this. So use that as our new x. Go and find a tangent at the point with that x coordinate on our graph. And then draw this new tangent. And if our function satisfies all the conditions that it needs to do, we'll discuss that. Then we should be able to, at that point, find a x-intercept that might be a good approximation. And if that x-intercept is still not a good enough approximation, we will continue doing this. And what's going to happen is we'll notice that the x-intercepts that we're finding are going to be closer and closer and closer to each other. And at some point, they will converge to a value which will be a good approximation to the x-intercept of the function that we are looking at. So now let's look and see how the actual operations here will work. So if we go back and look at our function and start with any value x sub 1 and draw a tangent line at x sub 1 f of x sub 1, and then try to find the x-intercept for that tangent line. So our first equation, the equation of a tangent line, is going to be y minus f of x sub 1 equals f prime of x sub 1 x minus x sub 1. And then to find the x-intercept, we will need to plug in 0 for our y, and we'll get an x sub 2, that a certain value for our x-intercept. So our equation is going to start looking like this, where the y is replaced with 0, because the y coordinate of that point is 0, and whatever the x coordinate is, we would have solved for. And we can rearrange this equation, divide by f prime of x sub 1, and then move things around. And we end up with this equation solved for x sub 2. So x sub 2 could be found by taking x sub 1 and subtracting the ratio of f of x sub 1 and f prime of x sub 1, as long as the derivative is not 0, right? Otherwise, this will become undefined, right? So next thing we're going to do is then see if we can repeat this process, right? So we'll use the new value that we have, x sub 2, find x sub 2 f of x sub 2, and draw a new tangent line, and find its x-intercept of x sub 2, x sub 3, right? So our these points that we had, x sub 1, x sub 2, x sub 3, are going to create a sequence. And that sequence, if it converges, we are going to be able to find our solution or the root to our equation. So in general, we are going to continue doing this and get the sequence x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n, as long as the derivatives are not equal to 0. And once that sequence converges, we have our solution. Now, it could happen that this method doesn't work. If our derivatives end up being close to 0, our tangent lines may become very close to or being horizontal, and our x intercepts may be very, very far away. In those cases, sometimes it helps to start with a different initial x sub 1 and then retry this. And it's also possible that our equation doesn't have a solution at all. And as we try to find this sequence, the sequence actually diverges. Okay, so let's look at an example, see how Newton's method works by looking at a function that Newton himself used to demonstrate the effectiveness of his method. So here we have a function f of x equals x cubed minus 2x minus 5. And first thing we're going to do is take the derivative. So the derivative is going to be 3x squared minus 2. And then rewrite the equation like we saw earlier in terms of x sub n plus 1. So we will have x sub n plus 1 is equal to x sub n minus f of x sub n, and f prime of x sub n goes in the denominator. So that's how our function is going to look like, or our points are going to look like. So next thing we're going to do is pick a value. And again, I'm going to use the value that Newton himself used. He started with x being 2. Right, so sometimes that needs a little bit of experimentation to see what starts to converge faster, and maybe find a different number. So 2 happens to work rather well here. If we start with x sub 1 being 2 and plug it into our function, we'll get that x sub 2 is going to be 2 minus 2 cubed minus 2 times 2 minus 5 divided by 3 times 2 squared minus 2. And that evaluate gives me 2.1. So notice our x sub 1 was 2, x sub 2 is 2.1, so there wasn't much of a change there, which means that was a pretty good guess, right? So as we discussed, this sequence needs to appear to be converging for us to have a solution. So we'll go ahead and find our x sub 3 by using 2.1, plugging it into our x sub n plus 1 formula. So we get x sub 3 is 2.1 minus 2.1 cubed minus 2 times 2.1 minus 5 divided by 3 times 2.1 squared minus 2. And that gives me 2.0946. So again, notice from x sub 1 to x sub 2, there was a change of a 0.1. From x sub 2 to x sub 3, that changes, and now all the way to the second decimal place. So we have about 0.01 change. So that sequence looks like it's converging, and that's 2.0946 is a pretty good approximation to our solution. If we need more accuracy, we can continue and find another iteration, and we'll get closer to the correct